Welcome back to che205. So we continue our discussion today on special matrices, and then we're going to look at how we can solve a linear system using matrix package in Excel. Last time we talked about symmetric matrix, diagonal matrix, and today we're going to talk about three-diagonal matrix. So if you remember, diagonal matrix is a matrix whose non-zero elements are sitting on the diagonal. In other words, off-diagonal elements are zero. In three-diagonal, we have non-zero elements sitting on the diagonal, which is, let's say in this case, these two. These are diagonal elements. Then super-diagonal is this one or these ones, and then sub-diagonal is these ones or are these ones. Okay, so in three-diagonal matrix, we have to have non-zero elements along the diagonal, super-diagonal, and sub-diagonal. In other words, any other elements should be zero. Like we get zeros here and here, but on the diagonal, super-diagonal, and sub-diagonal, we should have non-zero. That doesn't mean that you should not have zero on the diagonal. You can have zero on the diagonal, but you have to have at least one non-zero elements along the diagonal, sub-diagonal, and super-diagonal. Okay, so in other words, the elements above the sub-diagonal, right, and the elements below this, above the super-diagonal and below the sub-diagonal, which are these ones and these three ones, these should be zero. So this is called three-diagonal matrix. Okay, and by the way, three-diagonal matrix has to be square, because I mean, if this is not square, you cannot even define diagonal. Okay, another matrix we're going to talk about is orthogonal matrix. Orthogonal matrix is a matrix such that when you get transpose of it, you multiply by itself, you get identity. Okay, so we can easily make a orthogonal matrix. Let's look at one example here. Alright, so let me open a spreadsheet and increase the font. Yeah, 12 is good. So let's make an orthogonal matrix. Let's say 1, 2, 2, and then 0 here. Let me make it like -1 here. Let's see if this is okay, so this is a orthogonal matrix, and this number actually is 1 over square root 2. This one is again 1 over square root 2. This is 1 over square root 2, and this is negative 1 over square root 2. And let's test whether this is orthogonal. So I'm going to apply my matrix package here. I'm going to go and activate it again. So add ins, select, and then I have to refer to the location of the matrix that I unzipped. As we discussed, I think this should be on your desktop. Alright, so this is it. I'm going to click on that, and I'm going to click yes, and then OK. Then I get this blue button here. I'm going to click on that. I get this ribbon. I'm going to move the ribbon over here, and then I'm going to go to macros, matrix operations. I want to do the transpose. I'm going to click on the transpose, and then I introduce my original matrix here in this blank area. So I highlight this, and then the result would go to this cell. So I'm going to click on this blank cell, then on this blank area, and then on this blank cell. So this picks up the address for this cell. It's going to be here, and then run. All right, so this is the transpose of it. You see you read rows and you write it as columns. So this is the first row, is going to be first column. This is the second row, and this is going to be second column. I'm going to multiply this by that and then put the result here, which should be identity. So when I click on multiplication, our first matrix is the same. The second matrix is going to be in this matrix. And alright, so there you go. So this is the first matrix over here. This is the second matrix, which is now the transpose of the first. Goes there. And then I want to have the result. I'm going to clear this up, hit backspace, and then click here, and then run. You see that it's identity. So this multiplied by that is identity. That means the original matrix is orthogonal. So I hope this defines and makes it clear what we mean by orthogonal matrix. Transpose times the matrix itself should be identity. Alright, next topic we're going to talk about is solving linear system. Let's say we want to solve this system. We have 3 unknowns and 3 equations. And this is linear because we don't have second power of any variables. We don't have multiplication of the variables. The power for each variable is 1. Okay. So to do that using matrix package, first we create the matrix for the coefficients. Okay. So the coefficients, after we move all the variables to one side, like all variables are on the left side of the equal sign, then the coefficients for the first equation is 1, 1, 1. For the second one is 1 minus 2 plus 2. And 1, 2, minus 1 for the third equation. So let's write them in a matrix. Okay, so I'm going to close this, clear this up. Alright, the first matrix was 1, 1, 1. So that's the first row. Let's go back here. 1, 1, 1, then it's 1 minus 2, 2. 1 minus 2, 2. And then 1, 2 minus 1. So here's 1, 2 minus 1. And then in the next column here, I'm going to write the right side of the equations here. We call it B vector. So let's say the coefficient for the matrix for the coefficients is A matrix. And the constants on the right side, let's say that's a B vector, it's 0, 4, 2. It's a column vector, so we're going to write it at 0, 4, 2. Alright. So this is A. Let's just call it A. I'm going to merge these cells. This is A. This is B. And I'm going to have my solutions, let's say here, X. Okay. So A times whatever I have to get here, which is X, A times X should be B. Okay. The way to solve it is you go to the matrix package here, you go to macros, and then you click on system AX. Okay. Now here, first we have to define the A matrix. I'm going to click on the blank area here, then highlight A. Then we're going to go to B vector here, and then highlight B, which is this column vector. And then for C, starting cell, right? So the starting cell of C is going to be this. So X is going to show up right in this column. And then I'm going to hit enter or run. There you go, that's the solution. So A times X should be B. So let's test it. So now I'm going to multiply my A, which is this one, now times the solution. So solution is this vector, right? So now I'm multiplying A, this 3 by 3 matrix, by X, I should get B. And then I'm going to write the result, let's say, here. Okay? And then click run. And you see that this is exactly the same as that. I mean, 4 times 10 to the minus 16, that is almost 0. Which is same as 0, and then 4, same as this 4, and 2 is same as this 2. So B is identical to this, which means A times X is B, which means X is the solution of the system. So this is how we solve the system using matrix package, alright? It's fairly easy as long as you install it, okay? Let me see. So we talked about the matrix. Now determinant. Well, in the textbook, there's a section 372, that talks about how to get the determinant of a matrix using row operations. I'm going to skip that. I think this is a bit off the topic, so we're not going to cover that, and you're not responsible for that during the exam. Gauss-Jordan elimination, you don't want this. I mean, as long as you know how to use the matrix package, then you don't need to do this. This is basically solving a linear system manually. And same thing with Gauss-Jordan. So we're gonna skip this section as well, again, because we know how to solve the system using the package. All right. So the next topic is rank of a matrix. To find the rank of a matrix, we need to decompose the matrix into something which is called SVD, or singular value decomposition. Actually, that is also covered in the textbook somewhere later in the chapter. Let me go down, even further down, right here. So SVD is discussed here, but I think we're going to talk about it now if you want to find the rank of a matrix. So let me go back to section 374. Okay, so to find the rank of a matrix, what we do is we decompose the matrix into three matrices, which is called SVD, and that is again in the matrix package here. Let's say if I want to find the rank of this 3x3 matrix, let me close this and clear up extra information that we don't need here. And these ones. Alright, so let's say I have a matrix like this. I want to define its rank. So what I do is I go to matrix package, matrix operation, and then I'm going to click on SVD here. Okay. Then in the blank area for matrix A, I select my matrix A, that's 3x3. And then starting cell, I want to have the result, let's say starting from here. And click on that. So first you click on this blank area, then click on the cell that you want to have the result at. And then click run. So there you go. It gives you three components. One is singular values, which is called S matrix. Sorry, so the singular values are called D matrix according to the text. So these are the D's. Let me just close this. So this is basically D matrix, and D stands for diagonal. So think of this as a diagonal matrix with only three elements along the diagonal. The rest of them are zero, so we don't show the zero. This is otherwise a 3x3 matrix because it has three values. The original diagonal matrix is a 3x3, and these are just the diagonal elements. The off diagonals are zero. And this is U, which is so I think in this nomenclature, they, instead of having SVD, they have it UVD. So basically we decompose the matrix. Original matrix is A, we decompose it to U times V times D. Let me just double check in the text. Let's go down. So this is SVD. Yes, so that's right. So the matrix will be decomposed into U, D, and V transpose. So in other words, your matrix A can be formed by multiplying U times D times V transpose, and this is E, this is D, this is U, and this is V. So it's basically going to be U times D times V, let's say transpose like this. This is the D, this is the U, and this is the V. Now, this is done by matrix package. If you want to find the rank of a matrix, we look at the D values, and the rank would be the number of non-zero D values. So in this case, I have three non-zero values. The rank of matrix A, the original matrix, is 3. Okay. All right. So thanks for watching. Stay tuned for the next video on rank of a matrix and solving linear system using matrix package.